In the early 1970s, astronomers believed they had a solid understanding of how galaxies move. Galaxies expand away from each other as the universe expands. The farther a galaxy is, the faster it should be moving away from us. This relationship, known as Hubble's law, had been confirmed again and again. But then something didn't fit. When astronomers measured the motion of nearby galaxies, they noticed an extra movement layered on top of cosmic expansion. Entire groups of galaxies, including our own Milky Way, were drifting in a specific direction. Not randomly, not slowly, but together. This extra motion was called peculiar velocity, movement that could not be explained by expansion alone. At first, the data looked like noise, measurement error, calibration problems, distance uncertainties. Astronomers assumed the anomaly would disappear as instruments improved. It didn't. As more data accumulated, the pattern became clearer. Galaxies across hundreds of millions of light-years were flowing toward the same region of space. Something massive was pulling them. And the strangest part? That region lay behind the dense dust of the Milky Way itself, a part of the sky astronomers call the zone of avoidance, where visible light observations are nearly impossible. We were being pulled toward something we couldn't see. This wasn't a single galaxy. It wasn't a known cluster. Whatever it was, it had to be unimaginably massive to influence motion on such a scale. Astronomers gave it a temporary, almost unsettling name: the Great Attractor. Seeing the Great Attractor directly was impossible at first. The Milky Way's disk is filled with gas and dust that blocks visible light. Entire regions of the universe are hidden behind it. For decades, astronomers simply had no way to look through this barrier. So they changed strategy. Instead of visible light, they turned to infrared and radio observations, which can pass through dust more easily. Massive galaxy surveys began to map regions that were once completely dark. Gradually, shapes emerged: clusters of galaxies, dense filaments, massive structures hiding behind the Milky Way. One of the most important discoveries was the Norma cluster, a gigantic cluster of galaxies located about 220 million light-years away. It was far more massive than initially expected and lay almost exactly in the direction of the mysterious pull. But even the Norma cluster alone wasn't enough. The pull was too strong, the motion too coordinated. As maps expanded, astronomers realized something even bigger was happening. Galaxies were not just falling toward a single cluster, they were flowing along enormous filaments like rivers of matter toward a deep gravitational basin. This led to a larger revelation. Our galaxy is part of a supercluster, not a small one, but an enormous structure containing over 100,000 galaxies. This structure was named Laniakea Supercluster, meaning immense heaven. And at its center, not necessarily a single object but a gravitational low point, lies the region we call the Great Attractor. It wasn't a monster hiding in the dark. It was a landscape. To understand the Great Attractor, astronomers had to change how they thought about gravity on cosmic scales. They stopped looking for a single object. Instead, they began mapping gravitational basins, regions where matter is so densely concentrated that galaxies naturally flow toward them, much like water flowing downhill. The universe, on its largest scales, looks like a cosmic web. Long filaments of galaxies connect dense nodes, surrounding vast empty voids. Motion within this web is not random. It follows the shape of gravity itself. The Great Attractor is not a point. It is the deepest part of a gravitational valley inside the Laniakea Supercluster. Our Milky Way, along with the Andromeda Galaxy and thousands of others, is slowly sliding along this valley, at a speed of about 600 kilometers per second. That motion is measurable even in the afterglow of the Big Bang, the cosmic microwave background, where it appears as a tiny temperature difference caused by our movement through space. This realization resolved a major mystery. There was no violation of cosmic expansion, no unknown force, just gravity, operating on a scale so large that humans had never mapped it before. The Great Attractor wasn't breaking the rules, it was revealing them. So why did this discovery take so long? Because nothing about the Great Attractor announces itself clearly. It doesn't glow brightly. It doesn't emit powerful radiation. It doesn't sit neatly in one place. It reveals itself only through motion. Astronomers had to measure galaxy distances with extreme precision, subtract cosmic expansion, and detect tiny deviations in velocity. Small errors could completely hide the signal. They also had to overcome the Milky Way itself, our home galaxy acting as an observational blindfold. Only with large-scale surveys, better distance indicators, and advanced computational models could the picture finally come together. The Great Attractor wasn't discovered in a moment. It emerged slowly as data accumulated and patterns became impossible to ignore. And even now, it is not finished. As surveys improve, astronomers continue refining the map of Laniakea and the flows within it. Some evidence suggests even larger structures may lie beyond, influencing motion on scales we are only beginning to understand. This is how modern astronomy works, not through sudden revelation, but through patience, accumulation, and correction. And in the process, we learn something profound but simple. Our galaxy is not drifting freely through space. It is part of a vast cosmic current. For most of the 20th century, galaxy motion seemed simple. Edwin Hubble had shown that the universe is expanding. Galaxies move away from each other, and their speed increases with distance. Measure a galaxy's redshift, estimate its distance, and you can predict how fast it should be receding. This worked remarkably well, until astronomers started measuring motions more precisely. When distances were refined using standard candles, objects with known brightness, astronomers noticed something odd. Many galaxies were not exactly where Hubble's law said they should be. They were moving slightly faster, or slower, or sideways. These deviations were not random. Entire clusters shared similar extra motion. This additional movement was labeled peculiar velocity, velocity not caused by cosmic expansion but by gravity. At first, the deviations were small, easy to dismiss. Distance measurements are notoriously difficult in astronomy. A small error can change everything. But as datasets grew, patterns emerged. Galaxies across vast regions were drifting in the same direction, like leaves floating downstream. The effect became impossible to ignore. This was not local gravity from a nearby cluster. The scale was far too large. Something massive was shaping motion over hundreds of millions of light years. And the only way to understand it was to stop thinking in two dimensions and start mapping the universe in three. To measure the pole, astronomers needed a three-dimensional universe. Not a picture, a map. This meant combining distance measurements with precise velocity data for tens of thousands, and eventually millions, of galaxies. Redshift surveys became the backbone of modern cosmology. By measuring how light stretches as galaxies move away, astronomers could estimate distance. By correcting for expansion, they could isolate true motion caused by gravity. But there was a problem. A large portion of the sky was missing. The Milky Way blocks nearly 20% of the visible universe. Dust clouds scatter and absorb light, creating a blind region known as the zone of avoidance. To see through it, astronomers turned to infrared and radio wavelengths. These forms of light pass through dust more easily, revealing galaxies hidden behind our own. Slowly, the blank space filled in. Clusters appeared where nothing had been before. Filaments connected structures across the sky. What once looked like random motion now followed clear paths. The universe began to look less like a scatter of points, and more like a network, a cosmic web. And the Milky Way was clearly moving along one of its strands. Once the 3D map existed, astronomers could finally ask the right question. Not what is pulling us, but where does everything flow? By tracing galaxy motions backward, scientists reconstructed gravitational flow lines, paths galaxies follow under the influence of mass. The result was striking. Galaxies were not simply orbiting clusters. They were streaming along enormous channels, converging toward a central region. This region was not a single object but a gravitational low point, the deepest part of a massive basin. That basin defines the boundary of our home supercluster, Laniakea Supercluster. Everything inside Laniakea flows inward. Everything outside flows elsewhere. The Great Attractor is the name given to the direction of that inward flow. It is not a wall, not a point, not a mystery object. It is the destination gravity naturally leads to within this structure. Our Milky Way is moving toward it at about 600 kilometers per second, a motion detectable even in the subtle temperature imbalance of the cosmic microwave background. The pole was never invisible. We just didn't know how to look for it. By the time the Great Attractor was fully mapped, the mystery had transformed. What began as an unexplained motion became a measurement problem, and then a solved one. The key wasn't a new force. It wasn't exotic physics. It was scale. Humanity had never before mapped gravity on such enormous distances. Once we did, the motion made sense. Modern cosmology now routinely uses cosmic flow measurements to refine models of large-scale structure. Supercomputers simulate how matter clumps and moves. Telescopes survey deeper and wider. The Great Attractor no longer surprises astronomers. but it changed how they see the universe. Not as static clusters drifting apart, but as a dynamic landscape shaped by invisible valleys of mass. Every galaxy has a path. Every path follows gravity. And gravity, on the largest scales, draws maps we are only beginning to read. By the time astronomers understood the structure of Laniakea, one misconception still lingered. The name Great Attractor sounded like a single object, something massive, mysterious, and compact. A cosmic monster hidden behind the Milky Way. That idea is wrong. The Great Attractor is not one thing. It is a region. At its core lies a concentration of galaxy clusters, the most significant of which is the Norma cluster. This cluster alone contains thousands of galaxies and a mass equivalent to tens of thousands of Milky Ways. But even Norma is not the full story. Surrounding it are additional clusters, groups, and filaments of matter, all contributing to the same gravitational pull. Together, they form a deep gravitational basin within Laniakea. Think of it as a valley, not a point. Galaxies do not fall toward a single destination. They slide downhill along the curved shape of spacetime created by all this mass combined. The reason the Great Attractor feels so dominant is not because it is unique, but because it sits at the lowest point of our local gravitational landscape. From our perspective, buried behind the Milky Way's dust, it remained hidden for decades. But once infrared and radio surveys revealed the region, the picture became clear. The pull came from structure, not mystery. One of the most important results of mapping the Great Attractor was defining a boundary. Not a wall. Not an edge you can see. A boundary of motion. Astronomers discovered that galaxies inside Laniakea all flow toward the same gravitational basin. But galaxies just beyond a certain region do something different. They flow elsewhere. Some move toward the Shapley Supercluster, an even more massive structure lying farther away. Others follow different filaments entirely. This revealed something profound but practical. Superclusters are defined not by shape, but by motion. Laniakea is not just a collection of galaxies. It is a system with a shared destination. Our Milky Way sits well inside this system, about 250 million light-years from its center. That distance may sound vast, but on cosmic scales, it is firmly inside the valley. This discovery reframed our address in the universe. We do not live in an isolated galaxy cluster. We do not drift randomly. We are part of a structured flow, one region among many in an even larger cosmic network. And Laniakea itself is not the end of the story. It is just one basin among countless others. Once astronomers accepted that the Great Attractor was part of a larger structure, a new question emerged. Is it the biggest thing around? The answer appears to be no. Beyond Laniakea lies the Shapley Supercluster, one of the most massive concentrations of galaxies known. Its gravitational influence may extend across more than 1 billion light-years. Some studies suggest that Shapley contributes to the motion of Laniakea itself, a pull acting on the pull. This doesn't mean there is an endless chain of attractors, but it does mean that cosmic structure is hierarchical. Smaller basins sit inside larger ones. Motion compounds across scale. At some point, the pattern must end, limited by the expansion of the universe itself. But we are still mapping where that limit lies. Every time surveys expand, the universe reveals new structure, new filaments, new basins, new flows. The Great Attractor was not the final discovery. It was the first clear demonstration that gravity shapes motion far beyond what humans once imagined. The Great Attractor changed astronomy in a quiet way. It did not introduce a new particle. It did not overturn physics. It did not require exotic explanations. Instead, it forced astronomers to accept a simple truth. The universe is not static. It is moving, everywhere all the time, shaped by gravity on scales so vast they are difficult to comprehend. Galaxies are not just expanding away from each other. They are also falling inward, sliding along invisible structures defined by mass. The Great Attractor taught us how to see that motion. Today, cosmic flow studies are standard tools. They help refine cosmological models, test simulations, and improve our understanding of how matter assembled after the Big Bang. What once looked like an anomaly is now a reference point. And the lesson is clear. When something doesn't fit our models, the universe is rarely wrong. Our maps are. The Great Attractor wasn't hiding. We simply hadn't learned how to draw the universe correctly yet.